Hello, this is John Byes for Edinburgh Explorations, put out by the School of Mathematics and also the School of Physics and Astronomy here at the University of Edinburgh. And this is my third show on the standard model of particle physics. So in the first show, I just talked about various particles that were discovered over the course of the 20th century and how they fit into the standard model. The second one was a bit more about the concepts that led up to the standard model, starting with the three big pillars of classical physics in the late 1800s and how their internal contradictions forced ultimately the development of special relativity and quantum mechanics, which were then synthesized into what's called quantum field theory, which is the framework in which we can write the standard model of particle physics. So I said a little bit about special relativity and very little about quantum mechanics. Special relativity alters our concept of space and time, and I said how it unifies space and time into a concept of space-time. Quantum mechanics, I didn't say much about at all, and that's what is the subject of the talk today. Quantum mechanics is much more radical. It alters our concept of logic. Somehow it's easier to get used to modified concepts of space and time than it is modified concepts of logic, because when you modify logic, the very concepts of what it means to say something or see something change. They mean something different now. And that takes quite a while for people to get used to. So it's very hard to summarize the idea behind quantum mechanics in simple terms, like it was for special relativity. So that's my challenge now, is to begin diving into that, and that's going to take several episodes. I'm going to try to phrase it in terms of the standard model and what we can do with a standard model. So let's go that way. So you will hear repeatedly that the symmetry group of the standard model, the so-called gauge group, is U1 times SU2 times SU3. Each one of those is a group. A group describes ways you can change a situation that are reversible. And these three groups combine together to form a larger group, which is called the symmetry group, or often the gauge group of the standard model. And so we're going to have to get into that in quite a lot of detail, but I'm not really going to talk much about groups yet. For now, I'm just going to talk about quantum mechanics, but we'll see that it's connected to these three groups. So these three groups, whatever they are connected to three different kinds of forces. It's a bit tricky, but let's just dive in there. So there's the electromagnetic force, which is the simplest one, the one that was described by Maxwell's equations, which were understood in the 1800s. Then there's the weak nuclear force, which is responsible, for example, for how a neutron can decay into a proton and an electron antineutrino. And then there's the strong nuclear force, which holds the quarks together to form particles like neutrons and protons. Now, the weak force is all about qubits, in fact. So you may have heard about qubits when you're learning about quantum computers. So ordinary classical computers use bits, say 0 and 1, to describe information. A qubit is a quantum bit. What it has in common with a bit is this idea of a binary alternative, a choice between two alternatives. And that two there, the two alternatives, is connected very strongly to this two in SU2. I'm not really going to explain what SU2 is today, but it's about qubits in a certain way. Similarly, the strong force is about qutrits. That's a funnier word. A trit is about a threefold alternative when you're choosing between three different possible things. A qtrit is the quantum version of that. And those three things are the reason for the three in SU3. Now, what about the electromagnetic force? Why did I skip that one? Well, that one's sort of weird because, well, you see there's a one here. So the electromagnetic force, you'd have to say, is about Q units. The term Q unit is rather rarely used, but it is used sometimes. And that's the quantum version of a choice among one alternative. Now, a choice among one alternative doesn't seem like much choice at all, right? So it's like you say, you've got a choice of breakfast today. You have to eat toast. That's your choice, just one choice. That's a choice among one alternatives. It doesn't seem like there's anything going on there, but in fact, there is still something going on there in the quantum case. Now, the qubit case first came up when people were studying spin. There's the idea of a spin 1/2 particle like an electron, and an electron, which I'll use as just my example, can have spin pointing up or pointing down. That is, if you measure the angular momentum of an electron in the vertical direction, and the electron is more or less at rest, then you discover that its angular momentum can be pointing up, and it has a certain magnitude, fixed magnitude, or it can point down, and it has a certain magnitude. This is the binary alternative you get when you measure the electron's angular momentum along the z-axis, the vertical direction. It's a remarkable feature of quantum mechanics that you have just those two alternatives when you measure the spin along that particular axis. Now, that's only indirectly connected to the weak nuclear force, but when Heisenberg began very early work on the weak nuclear force, he made an analogy between the spin of an electron being either up or down and another binary alternative, which was what was concerning him. Namely, he noticed that protons and neutrons were very similar to each other. They have different electric charge, but that's all about electromagnetism, which is over here. If you focus on the weak force, the proton and the neutron seem very similar, and they also have a very similar mass. And so he thought, why don't I use the math that people use to describe spin up or down to describe whether some particle is a proton or a neutron? So he made up a name for this modified theory that uses some of the same math, and he called it isospin. So nowadays, we still follow that line of thinking that the weak force is about isospin, which involves studying particles where there's a binary alternative between being isospin up or isospin down. So what is isospin? Well, it's a mysterious thing, but the proton and the neutron differ by one of them having isospin up and the other having isospin down. We're going to talk about that a lot more. I'm just getting started. And there are other particles for which that binary distinction applies. Namely, I already mentioned that the electron neutrino is somehow similar to the electron, and they too are two particles, one of which has isospin up and the other has isospin down. This became even more clear when we discovered that protons and neutrons were actually made up of quarks, and they're both made up out of three quarks, and two of the quarks are the same, and the difference is that in the proton, the third quark has isospin up, whereas the neutron has a quark with isospin down. And so those two kinds of quarks, once they were discovered, were naturally given the names up and down, or U and D. And protons and neutrons are not considered fundamental particles anymore, but the neutrino and the electron and the up and down quarks are, and the main difference within each pair there is this binary alternative of having isospin up or isospin down. But they're described using quantum mechanics, so this binary alternative is not described using an ordinary classical bit, like true or false, but it's described using a qubit, quantum bit. I will have to explain to you, and I will today, what is a quantum bit. How about the strong force? The strong force is about a property that quarks can have, which I haven't said much about yet, called color. It's called color for the following reason. It comes in three kinds. There's a three-ary alternative here as opposed to a binary alternative. The color of a quark can be of three different kinds, and people needed to make up names for these three kinds. It's nothing like anything you observe in everyday life, but just for fun, people call those three colors red, green, or blue. So I repeat, that has nothing to do with the actual colors you see with your eyes, red, green, and blue. They're just convenient names for three different alternatives. And so the strong force, as we will eventually see, is all about this three-ary or ternary alternative, i.e. it's about a qtrit. And this group, SU3, is about how you can change a qtrit in a reversible way, just as this group SU2 is all about how you can change a qubit in some reversible way. Now, what about electromagnetism? Now that one starts seeming a little bit weird because that's the one where you just have one alternative. And so it seems like there's nothing to say, but it turns out that while classically, when you have just one alternative, there's really nothing much to say about it. But for a quantum unit, there is still some choice, and that's called phase. So if you have a Q unit, it can have various phases. A phase is a point on the circle. That's why I'm waving my hand around like this. A phase is a point on the circle, and we often think of that circle as the unit circle, and we often think of that unit circle as living in the complex plane. In any event, you can take a Q unit and you can rotate it by thus changing its phase, and that has a very subtle effect on it, even though in some sense there's just one alternative here. So in some sense you're not changing anything much at all, but there's still a subtle kind of change going on. For example, when we learn about energy in quantum mechanics, we discover that when you think nothing is going on, that is, when you think you have a physical system that has some fixed energy and is not changing at all, in fact, it is changing in a very subtle way. Its phase is changing, and its phase is changing, i.e. rotating, at a rate equal to the energy of the system. So part of what we now know in quantum mechanics, one of the stunning discoveries in quantum mechanics, is that energy is just the rate of change of phase. And we can see that happening even in the simplest of situations where you have a Q unit. For a Q unit, that's all that's going on, is the phase can change. And the electromagnetic force is connected in an interesting way to phase change. Now, there are a lot of subtleties here, which I'm not getting into, so please don't sue me if you see that I'm leaving something out. But one thing I have to say is that you might think that the electromagnetic force is connected to this U1 and the weak force is connected to this SU2, and they have nothing at all to do with each other. But in fact, the electromagnetic and weak force are to some extent partially unified in the standard model into something that we call the electroweak force. And what's going on, which I don't really want to get into too much, is that the copy of the group U1, which is relevant for electromagnetism, is actually not the very visible U1 in this formula that I wrote on the top of the page. There's actually another way to stuff the group U1 into U1 times SU2, and that is the one that's relevant to electromagnetism. I'll get into that much more. That's very tricky, and that's really where the Higgs boson enters the scene, which is a more advanced topic than we're doing today. So today, I'm really just trying to get you the idea that when you deal with quantum systems, you may have a choice between several alternatives of what the system is like, but this choice is not described in a classical way, like by bits. It's described in a quantum way, which is much more subtle. Now, I'm going to talk a bit more about this now, but I just want to talk about it in the case of qubits. A whole bunch of what I'm saying would apply equally well to qutrits or to even more alternatives. So there's nothing special about the numbers 1, 2, and 3 when it comes to basic quantum mechanics. Those just happen to be the things that show up in the standard model. But because the number 2 is the smallest number that's not too ridiculously small, like 1, I'm going to talk to you now about qubits. So let's study qubits a bit, if you can stand the pun and not revolt. So let's study qubits. So what do I mean? Let's study qubits. I'm going to talk to you about how quantum mechanics works in the case of systems with two alternatives. So these are quantum systems with two alternatives. That is two different ways that the system can be. However, we will see that unlike the classical bits, as soon as you get two alternatives, there are some sneaky things that happen that essentially mean you get more alternatives that come in for free. So, but wait, don't just think it's only two alternatives. So let's dive in now and let's start talking about qubits. So let's in fact start by talking about classical bits as a warm-up. So a classical bit is a way of describing two alternatives, one of two alternatives. That is, if you have two alternatives and you want to say which one holds, which is the case, you can describe that by giving a bit. So in computers, you call those two alternatives 1 or 0. So a bit is just a 1 or a 0. But there's nothing sacred about those two names. In classical logic, those two alternatives are also called true or false. So it could be either true or false that it's raining today, if it's either raining or not. In quantum mechanics, we often think about two alternatives, which are the alternatives for the angular momentum of a so-called spin 1/2 particle, like an electron. And I think I'll just say electron from now on as an example. And an electron, when you measure its angular momentum along the vertical axis, its spin can be either up or down. So that's another name for the two alternatives, and that's the name that I will generally use. So that's all there is to it. I mean, I'm making up lots of names for the same thing, but this is a really simple concept, just like yes or no. That's another thing I probably should have said. Another name for these two choices is yes or no, right? Okay, next, I'm not going to do the quantum bit yet. I'm going to talk about something sort of halfway towards the quantum bit, and that's called a probabilistic bit. This is where probability theory enters our description of the universe. So here the idea is that there are two alternatives, but each one can happen with some probability. So we could have up with probability p, p is some number, and we could have down with probability q, some other number. Now those numbers can't be just anything. They have to obey some rules. So for example, when you talk about a probability, P or Q, they have to be real numbers. So we use this fancy looking R for the set of real numbers. And if you've studied some math, you know this funky looking symbol means that P and Q are members of the set of real numbers. So this is the membership symbol. But probability can't be just any old real number either. These probabilities, P and Q, have got to be numbers between 0 and 1. So when something has probability 1, you're sure it's occurring. When it has probability 0, you're sure it's not occurring. But then there's lots of numbers between 0 and 1 for situations where you're less certain about what's going on. So if you say there's a 30% chance of rain, then, and this up means rain, and this down means not rain, then P would be 0.3. That's 30%. These probabilities have to obey another rule, that is, they have to add up to equal 1. This is what's going on because we have just two alternatives. So it's either raining or it's not raining. For example, suppose it's clear cut, which is which, and there's no other alternatives. Then if P is 30%, then Q, the probability that it's not raining, has got to be 70% because 0.3 plus 0.7 equals 1. So hopefully you're familiar with probability to some extent. Probability theory is very deep and subtle. I'm not telling you, notice, what probability actually means here. I'm assuming that you have some idea of what probability means, and I'm just taking advantage of your existing knowledge on that rather than defining probability. Why? Because defining probability is actually quite subtle. We have all heard the idea that if a coin has a 30% chance of landing heads up, and the two alternatives are heads up and tails up, then if you flip a huge number of coins, then approximately 30% of them will land heads up. That's called the frequentist interpretation of probability, where you think of probability as describing the frequency with which some event occurs when you do repeated trials, when you set the situation up repeatedly over and over again, and you take the limit where the number of trials approaches infinity. There's also another interpretation of probability theory called Bayesianism, which is deeper, but I'm not going to get into any of that stuff now, except to let you know that if you do, you will manage to keep yourself busy for quite a while. I'm going to move straight on to something far more confusing, quantum bits. So let's look at the quantum bit or qubit. How does that work? Well, again, you have two alternatives. And again, I'm just going to call them up and down, but they could be anything. They could be raining and not raining. They could be the cat is alive or the cat is dead or whatever. That's not the point here. It's just that there are two alternatives and we want some convenient name for them. So I'm calling them up and down. Okay. So what's the deal? Well, in a quantum bit, you have up, not with a certain probability, but with a certain amplitude. Let's say it has amplitude alpha. Now I'm switching to Greek letters just to be more intimidating. And let's say it's down with amplitude. Well, I know that after alpha comes beta. That's why they call it the alphabet. So we'll use those two Greek letters for our numbers now. But what are these amplitudes? Well, there are many levels of answering that question, ranging from the shallow to the quite deep. I'm going to stick to being pretty shallow here. So I apologize for that, but you got to start shallow before you can get deep, right? So the first thing I want to say is that these numbers, alpha and beta, they're not real numbers anymore. We're not in Kansas anymore, as the saying goes. These are complex numbers now. So C, this fancy looking C with a little line in it, is our name for the set of complex numbers. They're not called complex because they're complex, believe it or not. They're called complex because they're made up out of two parts. They're a complex of two things. So a complex number is a way of describing a point in the plane rather than a point on the line, right? A point on the line, you can describe with one number. Point on the plane, you describe with a complex number. So here's a complex number, alpha. This little plane I'm indicating here is a picture of the complex plane. And the point is that this complex number really just involves two numbers, two ordinary real numbers. One is its x coordinate and one is its y coordinate. So this alpha here, all it really is two numbers, one that I'll call x, saying how far across you have to go from the origin to get to alpha, and the other one saying how far up you have to go. So what we do, though, that makes the idea of complex numbers so interesting is that we think of the two directions in the complex plane as being the ordinary real number direction and another direction called the imaginary direction, where it was called imaginary because it freaked people out for about 100 years. And so we write alpha as x plus I times y, where I is a unit vector pointing in the imaginary direction. So I is some funky new number which has the property that I squared is equal to -1. So at some point in the history of mathematics, people got fed up with the fact that there's no number that when you square it equals -1. So they just made up a number that when you square it equals -1, and they called it I for imaginary. And so a complex number has a real part, which is x in this example, and it has an imaginary part, which is y in this direction, in this example here, pointing in the vertical direction. Now, a quantum bit then will involve two things called amplitudes, which are complex numbers, but they can't be just any old complex numbers, just like probabilities couldn't be any old real numbers. They have to be two complex numbers that when you take their absolute values and you square those and you add them up, you get 1. So we read this as the absolute value of alpha squared plus the absolute value of beta squared is equal to 1. What's this absolute value baloney? Well, the absolute value of a complex number is just the length of this hypotenuse here. So the absolute value of alpha is just the length of this hypotenuse. Now, if you remember the Pythagorean theorem, good old Pythagoras, who didn't know quantum mechanics, still was able to figure out that length. And he said, hey, the hypotenuse is the sum of the squares of the two sides. So the absolute value of alpha is square root of x squared plus y squared. Notice that in our formula for what amplitude should obey when there are just two of them is that they should add up, their squares of their absolute values should add up to 1. So in some ways, it's the square of the absolute value, which is simpler. And you can see that it is because the square root goes away, and square roots are generally annoying. So the absolute value of alpha squared is just x squared plus y squared. Now, what is going on here, though? I mean, this is a bunch of math. This is like my 2-minute course on complex numbers. But what's going on? Well, I'll tell you what's going on. So first of all, what is a qubit? So a qubit, I will now officially define it. My underline is supposed to mean definition. And I will also sometimes call it a state. It is a quantum state of a system with two alternatives. Is just a pair of two complex numbers, alpha and beta, and they're complex numbers which have the property that I just said, that when you take their absolute values and you square them, they add up to 1. So that's what a qubit actually is. That's the definition of a qubit. Okay, that's one question answered, but there are lots of other questions. I started using this word amplitude, and I didn't say what the hell that meant. Well, amplitudes are complex numbers, but they're complex numbers where you do something in particular with them. So an amplitude, I will define now, sort of define. An amplitude, let's say like alpha, it's a complex number, but it's a complex number used to compute a probability. And the way you get a probability from an amplitude is you take its absolute value and you square it. So for that to even work, it's got to be true that this absolute value of alpha squared is between 0 and 1. Well, it will always be greater than or equal to 0, but it has to be less than or equal to 1 as well. So what we're doing here is we're taking a qubit and we're taking and it's a pair, alpha, beta, and then we take the absolute values of those and square them, and we require that sums up to 1. And whoops, you see a typo here. This has to equal 1. That's what I was trying to say. Sorry, I left that out before. So, so that's what's going on. And I might as well just say it because this is the key thing that everything else was just leading up to. So if you have a qubit, and let's pick one, I'll pick this one. We're talking about alpha beta, and you check to see if the alternative up is true. So remember, we're discussing a binary alternative where a system is either up or down. So if you have a qubit and you check to see if up is true, you get the answer yes. Yes, it is true with a certain probability, and that probability is the absolute value of alpha squared. So from what I've said so far, the role of the amplitude alpha is merely to compute this probability. That's not all there is to the amplitude. That would be sort of silly if that's all there was to it, but that's one of the things that it's good for. And then, of course, the same thing is true for down. So similarly, down will turn out to be true. That is, you'll see the system in this second alternative state with probability equal to the absolute value of beta squared. And those two numbers, absolute value of alpha squared and absolute value of beta squared, they sum to 1. So these are a coherent set of probabilities for a binary alternative. Okay, but that's just the beginning of the story because something funny is going on here. And what's funny is that there are lots of different choices of pairs alpha beta that give you the same probabilities, absolute value of alpha squared and absolute value of beta squared. So, but I will say there's more to a qubit than just those probabilities. There's more information in the qubit than just those probabilities. And this is what makes qubits different from probabilistic bits. So this is where things get funky. So, for example, first of all, there are ways to change the qubit that keep the probabilities the same. And here's one. You can take a qubit and you can multiply it by a phase say C. I'll tell you what a phase is in a minute. It's a kind of complex number. I'll tell you right now. I'll take you out of your suspense. So, so I will define phase. So what is a phase? It's a complex number, but not just any old complex number. It's a complex number where the absolute value equals 1. And you can multiply a qubit by a phase without changing the probabilities that the qubit represents, the probabilities for the system being up or down. So this is proof that there's more to the qubit than just those probabilities. Let's see how that works. So I'll take my qubit here, alpha, beta, and I'll multiply it by this phase. Now, hopefully you've studied a bit of vector math and you know how to multiply a vector by a scalar. But if you don't, no big deal. I'll just tell you, when you multiply a list of numbers by a number, it just means you multiply each entry in that list by the same number. So here I'm just defining this to this C of alpha comma beta to be C alpha comma C beta. Okay, so that's what it means to multiply a qubit by a phase. And then if you look at it, you'll see that these probabilities don't change. So the probability of being up is now the absolute value of C alpha squared. But if you do some calculations, or if you take a class on complex numbers, you'll know that the absolute value of C times alpha is the absolute value of C times the absolute value of alpha. And well, I've squared everything. And because a phase has absolute value 1, this is just the same as alpha squared. So we did not change the probability of the system being found to be in the up alternative when we multiplied its qubit by this phase C. Now, I realize now that I've never told you how to multiply complex numbers, and I've never explained why these rules are true. I don't think I want to do that right now. You definitely need to get good at complex number math to get good at quantum mechanics, but perhaps now is not the time for more of a course on complex mathematics, complex numbers. So please just take my word for it. Similarly, the probability that you find your qubit or your quantum system to be down after you've multiplied it by the phase is the absolute value of C beta squared, because that's the new second entry in our little list of two numbers. But the same kind of calculation works. And we see that the absolute value of C beta squared is just the same as the absolute value of beta squared. So we have not changed the probabilities at all for being up or down by multiplying the qubit by this phase. So that actually may illuminate some of the mysterious stuff I was saying when I was talking about Q units a while back. You may remember way back up here, I was talking about the electromagnetic force is related to Q units, where classically you're dealing with an alternative where you just have one alternative, which seems really stupid. And I said, well, there's still something interesting going on. You can take a Q unit and you can multiply it by a phase and get a new one. And that's true. And that's true for qubits, and it's true for qutrits, and so on. You can always multiply them by a phase and get a new one. There's a lot to say about that, but what I think I'll just say is just one thing right now, which is I just want to draw a picture of what phases are like. So here's a picture of the complex plane. So the phases are some of the complex numbers, namely the ones that lie on the unit circle. So a phase is a point on the unit circle. So here it is, and it has the absolute value of C is equal to 1. This is a phase. So there's a circle of phases, and it's the unit circle in the complex plane. And the set of all phases, that is this circle here, has a name. It's called U1. So when I began, I listed 3 different mysterious groups connected to the 3 forces in the standard model. One of those was U1, and now I'm revealing that U1 is just this circle, the circle of phases. Okay, but I'm talking about qubits now, actually, and what I'm telling you is that you can multiply any qubit by a phase and get a new qubit. However, there's more to it, more to the weirdness, because I said that you can multiply a qubit by a phase and get a new qubit with the same probabilities of being up or down. But there are other things you can do to a qubit without changing those probabilities. So let's look at that. So second, there are other ways that you can change a qubit without changing its 2 probabilities. Which are the absolute value of alpha squared and the absolute value of beta squared. Let's see an example there. So I'm going to show you a bunch of examples. And in fact, I'm going to show you a whole sphere of examples. So let me draw a sphere in 3 dimensions. So this is not the unit circle anymore. This is my pathetic attempt of drawing a sphere. There's the center of the sphere. Now, I said that if you're sure that your electron has spin pointing up, we denote that with a little arrow pointing up. So if the electron's spin is pointing up, then that corresponds to this point here, the north pole of the sphere. And that is a certain possibility for our qubit, where it's this qubit here. It's 1, 0. So 1, 0 says that the probability that your electron is spin up is 1, and the probability that it's down is 0. So it's definitely pointing up. So let's call that 1, 0 there, or we might call it also simply up. Similarly, pointing straight down corresponds to the qubit 0, 1, where now the probability is 1 that it's down and 0 that it's up. So a short name for this qubit is simply down. You're sure that it's pointing down. But there are lots of other points on the sphere, and amazingly, and this is really freaky, there are qubits that describe every point on the sphere in 3-dimensional space. I'm not going to fully explain this, but I do need to say a little bit about it to make my second point here. For example, What about this? Well, I'm not going to explain it to you, sorry, but if the electron spin is pointing to the right this way, that is, it's pointing along the x-axis, then there's a qubit for that, and it's 1 over square root of 2 times 1 comma 1. So we could call that qubit pointing right. And there's a qubit for an electron where the spin is pointing left. And that turns out to be 1 over square root of 2, 1 comma minus 1. So that is sometimes denoted with a little arrow pointing to the left. And you'll notice that there are lots more points on the sphere, and I'm not done with this business. But anyway, let's just look at those two. So we could ask, if an electron if its state, that is the way it is described by the qubit pointing to the right, that is this 1 over square root of 2, 1 comma 1, and now suppose you check to see if its spin is up. Perhaps I should be clear that though there are many things you could talk about for an electron, like how fast it's going, where it is, all sorts of stuff like that, here I'm only concerned with its spin, i.e. its angular momentum when it's more or less at rest. So I probably actually should be a little clearer here and should say something like this, not just an electron, but an electron's spin or angular momentum. So you have an electron where you know that the spin is described by this qubit pointing to the right, and you check to see if its spin is pointing up. Well, that's a weird thing to do, right? You have to admit that's a crazy thing to do. If I ask you like, hey, my finger is pointing this way, let's check to see if it's pointing this way. You would say, why bother? You know it's not pointing up, it's pointing to the right. But electrons are weird. Quantum mechanics is weird. We can check to see if its spin is up, and we get the answer, yes, it is pointing up with this probability. Remember, this little rightwards pointing arrow is short for this pair of complex numbers, 1 over square root of 2 times 1 comma 1, which is just a slightly shorter way of writing. Let's multiply it out. We get 1 over square root of 2, 1 over square root of 2. So that's our alpha in this case, and that's our beta. And so we know that the probability that something spin will be up is the absolute value of alpha squared, which is, in this case, 1 over square root of 2 squared, which is 1/2. So we get yes with probability 1/2, believe it or not. And people have checked that that's actually how it works in real life. So you can put an electron in a situation where you know its spin is pointing right, and then you do a measurement to check if its spin is pointing up, and you get, yes, it is pointing up with probability 1/2, which is incredibly freaky. Similarly, you can check to see if its spin is down. So the probability that its spin is down, when you check to see if its spin is down, is, well, now what we do is we take the absolute value of beta squared, but that's also 1 over square root of 2, because beta is also 1 over square root of 2 squared. So that's also 1/2. So when an electron spin is pointing this way, which for me is pointing right, then from my point of view, that's right. I don't know what you're seeing. I don't know if my screen has been reflected or not, but I'm calling that right. Okay. So when the electron spin is definitely pointing right, but we check to see if it's pointing up or down, we get up half the time and down half the time if we do this over and over again to different electrons. Okay, so it's crazy, but it's true. This is how reality actually is. This is why people get freaked out by quantum mechanics, but it's how reality is, so you got to get used to it. Okay, now that's fine and dandy, but what about this other thing where the electron's spin is pointing to the left? Let's do that. So what about electron spin pointing to the left? That's just short for, let's multiply it out, 1 over square root of 2 minus 1 over square root of 2. So now this is our alpha, 1 over square root of 2 is our alpha, and this is our beta in this new example. So the probability that you will see it spin up when you check to see if its spin is up, it'll be the absolute value of alpha squared. That is the absolute value squared of that first number in that little list. So that's 1 over square root of 2 squared. It's a half again. And for down, well, now we got a minus sign there. So we get minus 1 over square root of 2 squared. That's the only difference between this and last time. But when you square a minus sign, it goes away. So we still get 1/2. So we found two different states of the electron that both give you the same probabilities of being either spin up or spin down. That's freaky and true. And in fact, there are a lot more than just those two states that have a 50-50 chance of being either up or down. In fact, it turns out that all of these different possible ways that an electron can spin, where it's pointing in the equatorial plane here, sort of halfway between the North Pole and the South Pole, all of these guys here will correspond to some qubits, which I'm not going to bother writing down right now. And when you use those qubits, they will all have the same value of the absolute value of alpha squared and the absolute value of beta squared, but they will have different alpha and beta. So there's more going on in the qubit than just the probability of being spin up or spin down. So a qubit is much richer and more complex than a mere probabilistic bit. Now, you may be wondering a lot of things now. One of the millions of things you may be wondering is, how come spin right is 1 over square root of 2, 1, 1, and how come spin left is 1 over square root of 2, 1 minus 1? Where did those formulas come from? Well, I will tell you sometime the formula for how that works. And when I do, which it will not be today, apparently, because it's taken a while to get this far, when I do tell you that formula, then you will know how to answer all sorts of questions. So, for example, if I pick any old point on the sphere and I think of draw an arrow going from the center of the sphere to that point, and I ask you, hey, what's the quantum state or qubit for an electron that describes an electron whose spin is pointing that way? Well, if I describe that arrow using some numbers, some coordinates, then you will be able to crank out a formula to figure out what is alpha and beta for that qubit. So these four choices that I've shown so far and told you the formulas for are just some of the possible choices. And you will understand then much better than you do now, if you're just listening to this the first time, if you haven't already studied this stuff, you'll understand much better than you do now how this sphere popped out of thin air when we started studying qubits. Because something amazing has happened here, which needs better explanation than I've given so far. So the moral so far is rather shocking and not fully explained, but I'd better state it anyway. So the moral so far is that three-dimensional space emerges from studying qubits. More precisely, what I mean is that if you start studying a qubit, you just discover there are lots of qubits, and each qubit describes a possible spin for an electron or any other so-called spin 1/2 particle. And this spin can point in any direction, and it can point, it always has the same length, so it has to lie on a sphere like I'm drawing here, but it can point in any direction on this sphere. So this sphere comes from qubits. So here's a more precise way of stating the moral. Each point on the sphere comes from a qubit. And I haven't told you the formula for how that works, nor have I explained the rationale for that formula. But also, each point on the sphere actually comes from many different qubits, and those different qubits differ by multiplication by a phase. I'm not proving that, I'm just claiming that. In other words, the qubit, say alpha beta, which describes an electron whose spin is pointing this way, is just one of the qubits that could be used to describe an electron whose spin is pointing that way. You could take that qubit and you could multiply it by a phase, that is a complex number whose absolute value is equal to 1, and you'd get a new qubit that also describes an electron whose spin is pointing that way. So C times alpha beta, and also just plain old alpha beta, both describe an electron whose spin is pointing the same way. I'll just say electrons, one for this guy and one for that guy. So this is all very strange, okay? I'm not trying to explain everything, but I'm trying to tell you the basic facts. in such a way that doesn't cloak or hide the wild mystery of even a single qubit, a binary alternative. So this is the kind of reason why people find quantum mechanics difficult to wrap their minds around. I've thought about quantum mechanics ever since I started reading the Feynman lectures on physics. The third volume of the Feynman lectures is on quantum mechanics, and I was reading it when I was a junior in high school, working at a youth conservation corps camp where my job was to help people drag logs around in a park. Backbreaking work for me because I was an incredible wimp at the time. No muscles at the beginning. And my only pleasurable activity during that summer was trying to understand quantum mechanics. And that was tough too, because I had no knowledge. I was a mental wimp at that time. So that was, in a way, just as tough as dragging the logs around. But anyway, that was a long time ago, and I've been studying quantum mechanics ever since, and I think I understand it reasonably well now. And I feel sort of bad that I haven't really explained it too much so far, but I'm afraid that's inevitable because there's a lot to say. And so I think I'll just leave off here. This is a little bit about how qubits work. And I want to say much more about how qubits work and how quantum mechanics works in general, and then how qutrits work and how quunits work, and how those three, the quunits, the qubits, and the qutrits, are related to the three forces in the standard model. The three forces other than gravity are all described using this kind of strange picture of the world called quantum mechanics. So hope to see you next time, and we'll just keep on going.